Okay, so we can start back. So we're going to be building a motor in this section. Um, the idea behind a motor is that we want to be able to convert electrical energy into mechanical energy. So I'll first talk briefly about energy and power. So energy is the ability to do work. Work is the idea that you can, for example, lift an object up. So when I lift an object up, I'm essentially using energy in my body to do this mechanical motion to work against the force of gravity. So work is applying a force for a specific distance to essentially move an object. So energy is the ability to do work, and energy has many different forms. So we have electrical energy in a battery, mechanical energy such as a spinning flywheel, solar energy from the sun. We have gravitational energy. Like if you have water in a dam, the way that hydro powered systems work is that they have the water at high level and they allow it to fall, and that change in energy from the gravitational potential energy that does work, such as spinning a mechanical object to convert that into mechanical energy, or it goes into electrical energy. So that's energy. It's the ability to do work. Power is simply the rate at which electrical energy is being generated or being used. So in a power plant, they generate energy, so they convert. They're not creating energy just out of nothing. They're converting energy from one form to the other. So like a nuclear power plant, they're changing the energy that's contained in the materials into electrical energy. Solar power plant, they're changing solar energy into electrical energy. And then you use power in your house when you have like your microwave or your refrigerator. And typically in Illinois and across the country, you pay about 12 cents per kilowatt hour. So if I ran a 100-watt light bulb for 10 hours, then I use a kilowatt hour of energy. So it would cost me 12 cents to run my light bulb. So now we want to talk a little bit about electricity. So electricity is the form of energy that's due to the motion of the electrons. So I was briefly explaining to Evan. He asked a really great question in the break period, which is what actually moves in a circuit. So it's the electrons, which are the negative charges. They're the ones that move, but we keep track of the current, which is the motion of positive charge. So it's opposite the direction of the motion of the electrons. And so in order for us to transmit power, power is given by the product of current, which is the number of charges that move past a specific point per time, times the voltage, like in your battery. It's the energy per charge that your battery has. So power is the product of those two. So like in our house, when we run the vacuum, it's typically a high current device. It's like 5 amps of current, and it's operating at 110 volt AC. So overall, that's like 550 watts of power that the vacuum is consuming. So this power is given by the product of current times voltage. It's equal to, we're going to see a little bit later, there's something called Ohm's law that says that the voltage across a resistor is proportional to the current and proportional to the resistance. So the power is equal to current times voltage, or current squared times resistance. It's also equal to the voltage squared divided by the resistance. So in the early days, when people were deciding how to transmit power from the power plants to homes, there was a debate between whether this should be alternating current or direct current. And there was also some thought as to whether this should be done at high voltage or high current. Well, if you look at the formula for power, the challenge with delivering power from one location to the other is that the wires, even though they're very good conductors, they have to go thousands of miles. And so the resistance in the wire from going that sort of distance is such that it's better to operate at high voltage and have this term where the power that's being lost in the wire decreases as the resistance of the wire goes up. It's better to do that than to operate at high current, where you have the power that's lost in the wire increasing as the resistance goes up. So that's why the power lines have very high voltage and actually draw very little current along the wires themselves. Now, in order for us to use this very high voltage, this hundreds of thousands of volts, we need to safely step down that voltage to a level that can be used with household appliances. So the transformer, it's a series of magnetic wires, and it's a device that allows the conversion between one form of electrical energy to another form of electrical energy using the principle of electromagnetic induction. So we have a time-varying current in one of the coils that produces a time-varying magnetic field, and that therefore can create the spatially varying electric field and therefore transfer the power from a high voltage system to a lower voltage system, like 110 volts is lower voltage system. And then you can have higher currents because the power that you're transmitting is constant. You're not losing power you're not losing that much power as you go from the distribution plant to the transformer. And the transformer then does the last step conversion. It safely steps down the voltage from the high voltage lines that go overhead to something that can come into your house at 110 volts. So the ways that the systems of the electrical network work, you have the different sources of how you generate the power. So you can have a coal plant, you can have nuclear, you can have hydroelectric, you can have these medium-sized power plants. These produce very high voltages on the order of hundreds of kilovolts, so 100,000 volts. And then these signals are transmitted to, or they're transmitted on high voltage wires. So like you have 3 versus 2 at 110 kilovolts and higher. And then this is transmitted to local systems where the voltages are stepped down. So like to get to your house, you're going to step this down to 110 volts. And you may have other sources such as wind farms, solar farms, city power plants, and so forth. These are also providing energy into the system and providing power to power up society. Okay, so what we're going to do in just a bit is we're going to build this motor. So we're going to do this major project 15.1. So a motor is a device that converts electrical energy into mechanical energy. So we're going to apply the electrical energy from a battery, and we're going to get a wire to spin. That's going to be our motor. The generator does the exact opposite. So you need to, like, I don't know if anyone has been on these bicycles that you ride the bicycle and it turns on the fan or it turns on a light bulb, but you're changing your mechanical energy into electrical energy, which can then power other systems. So the way that we're going to build this motor is we're going to create an electromagnet, and the electromagnet is a magnet that's made by flowing current in a wire. We're going to use an electromagnet and a permanent magnet. A permanent magnet is something that you're probably more familiar with. The permanent magnet we're going to give you, it's inside your case of Oracle sorts. The permanent magnet exists even without having to apply a current to it. So we're going to use the permanent magnet to create a strong magnetic field. We're going to create an electromagnet, and the electromagnet is going to be special in the sense that as it spins, it's going to turn on and off so that it continues to spin. So the way that we're going to do this project, we're going to build this motor to understand how a magnetic field can rotate this electromagnet. And so the diagrams are a little bit different than what we're going to build. We've improved the way that these things are going to come out.